In an automatic control system, a controller initiates a corrective action based on the difference between the signal it receives and the set point for a controlled variable. The various types of corrective actions that controllers can provide are called control modes. With two-position control, a signal from a controller causes a final control element to move from one extreme to another, such as from on to off, or from fully opened to fully closed. To see how two-position control works, let's look at an illustration of a sump pump arrangement. In this system, a pump draws water out of a pit or sump. A float with a rod is the sensing element in the system. The float rod has two collars, which serve as stops for a linkage that connects the rod to a switch. It's part of an electrical circuit that starts and stops the sump pump motor. If the level in the sump rises, the float also rises, and the lower collar on the float rod pushes up the linkage to turn the switch on. This starts the sump pump motor. As the pump draws water out, the level in the sump drops, and the float moves down. When the water reaches the minimum level, the upper collar pulls down on the switch linkage, shutting off the pump motor. Now, in a two-position control system, a certain amount of change can occur in the process without causing a control system response. This amount of change is called the dead zone. The dead zone in this system is controlled by the positions of the two float rod collars. The dead zone can be reduced by moving the two collars closer together. A smaller change in level will then turn the pump on or off. But even though the water will be maintained at a more constant level, the pump will turn on and off more frequently. And this overuse could damage the system's components. With proportional control, a controller's output signal is proportional to its input signal. In other words, if the input to a proportional controller changes by a given amount, the controller's output will also change by a given amount. To explain proportional control, we'll use this illustration of an automatic level control system. We'll say that a temporary disturbance decreases the demand for water from the tank and causes the water's level to briefly surge above its set point. As the water rises, a level sensing float converts the change in level to mechanical motion. The motion is detected by a measuring element or transmitter and converted to a pneumatic signal representing the value of the higher water level. This signal is sent to the controlling element or controller. The controller measures the signal, compares the signal to set point, computes the difference between the two values, and produces a corrective output signal that's proportional to the input signal. The controller sends that signal to the final control element in the system, a control valve. The control valve responds by closing down to decrease the flow of water to the tank. However, because of process characteristics such as resistance, capacitance, and dead time, the level fluctuates before it finally returns to set point. We can tell more about how the temporary change in water level affected the system if we plot the control signals on a graph. On the graph, the scale on the far left is marked off in feet to indicate the water level in the tank. The next scale indicates the value of the input signal to the controller in pounds per square inch, or PSI. The scale on the right indicates the value of the output signal from the controller. It too is in pounds per square inch. The dashed horizontal line represents the set point for the water level. In this example, the set point is 3 feet, which is equivalent to a 9 psi input signal to the controller and a 9 psi output signal from the controller. In this case, it increased to 13 psi. The output signal caused the control valve to close, decreasing the supply of water to the tank. As the level in the tank fell, the input and output signals decreased accordingly. However, the process characteristics that we mentioned caused the signals to go through several fluctuations or cycles before returning to set point. With a temporary disturbance, process conditions return to their original state. So a proportional control system can normally return the controlled variable to set point. But If a continual disturbance occurs, a proportional controller may not be able to restore original conditions. For example, this graph shows the input and output signals when an ongoing decrease in demand caused the level in the tank to rise. In this example, the control system brought the process back under control. But when it did, the level stayed higher than the original set point. That's because the input signal to the controller increased, then stayed high because of the continual disturbance. As a result, the proportional output signal stayed high as well. The higher steady state value that resulted, that is, the higher level that's represented by the input signal, is called the control point. The difference between the variable's control point and its original set point is called offset. Offset occurs because a proportional controller produces only enough output to bring a process back under control during a continual disturbance. It may not produce enough output to overcome the disturbance and return the process variable to its original set point. In some processes, a proportional controller may not return a process variable to its original set point. In other words, the controller's action may result in offset. However, a controller adjustment can sometimes be made to change the amount of offset. This adjustment affects what is known as the proportional band, or PB. Proportional band is the amount of output change, or delta output, in relation to a given amount of input change, or delta input. The proportional band value is usually multiplied by 100% so that it can be expressed as a percentage. When a controller's input change and output change are equal, the relationship between the signals is 1-to-1, and the proportional band is 100%. This condition is called a 100% PB. The input and output signals on this graph show a 100% proportional band. Now, the signals on this graph show a proportional band that's less than 100%, otherwise known as a narrow proportional band. With a narrow proportional band, a small change in input to the controller produces a larger change in output. This relationship is equivalent to a 50% proportional band, since 1/2 times 100% equals 50%. With a narrow proportional band, control action is rapid, and the value of the controlled variable stays closer to set point. However, decreasing a proportional band setting increases the amount of cycling, which can overwork system components. Now, the signals on this graph show a proportional band that's greater than 100%. This type of proportional band is called a wide proportional band. With a wide proportional band, a large change in input to the controller produces a smaller change in output. The proportional band for this example is 200%. Since the output signal changes less than the input signal, a wide proportional band can minimize the amount of cycling in a system. However, there's more offset with a wide proportional band. Some manufacturers use the term gain when describing a proportional control adjustment. Gain is the inverse of proportional band, and it's expressed as a quantity rather than as a percent value. For example, a 1 psi change in input that produces a 2 psi change in output represents a 50% proportional band. But since gain is the inverse of proportional band, the relationship between the change in input and output is reversed. So the gain in this example is 2. In this topic, we examined two-position control and proportional control, and we looked at how those control modes work in an automatic control system. Now let's try some practice questions. Now, in a two-position control system, a certain amount of change can occur in the process without causing a control system response. This amount of change is called the dead zone. The input and output signals on this graph represent a proportional control system's response to a continual disturbance. Proportional band is the amount of output change, or delta output, in relation to a given amount of input change, or delta input. Not all control modes can return a controlled variable to set point after a process disturbance. However, reset control is designed to adjust the output of a proportional controller to help eliminate offset and restore original process conditions. Reset action responds to a controlled variable's deviation from set point by increasing or repeating the amount of proportional control until the variable returns to set point. Reset control doesn't exist without proportional control. In fact, it's actually proportional plus reset control, since it adds an additional corrective action to the proportional action. Also, reset control is sometimes called proportional plus integral, or PI control, because it's based on a mathematical function called integration. In any case, it's easier to understand how reset control works by looking at an example. In this arrangement, an automatic control system is used to maintain the level of water in a tank. The input signal from the transmitter to the controller represents the level of water. The output from the controller adjusts a control valve in the supply line to the tank. If a continual disturbance causes a decrease in the flow of water from the tank, the level in the tank rises, and the input signal to the controller changes to reflect the higher level. How do you suppose the controller responds to the change in level? The controller responds by signaling the control valve to close down. This reduces the flow of water to the tank and allows the level in the tank to gradually return to set point. We can get a better idea of how the system responded to the disturbance if we plot the input and output signals on a graph. We'll include a time scale on the graph to see more clearly how the control action works. During the first minute, the increase in water level caused the input signal to the controller to increase from 9 psi to 11 psi, which is a change of 2 psi. During the same 1-minute interval, a proportional-only controller with a 100% proportional band would have produced an output signal that matched the input signal. But the output signal from this controller includes proportional action plus reset action, and it increased to 13 psi, a change of 4 psi. What this means is that the reset part of the control action increased or repeated the 2 psi proportional action one time in 1 minute. This is sometimes described as 1 minute per repeat, or 1 MPR. As the level of water in the tank dropped, both signals decreased, then fluctuated briefly before returning to steady state. That's because the value of the controlled variable, represented by the input signal, returned to its original set point of 9 psi. In our example, a reset control action of 1 minute per repeat was able to return the controlled variable to set point. Often the amount of reset in a system can be adjusted. However, a reset that's too fast can cause a controller to overcorrect and cause the process variable to cycle out of control. In those cases, a slower reset may be needed. Rate control is a control feature that responds to the speed at which a variable deviates from set point. The faster the variable changes, the greater the amount of rate control action. Rate control is normally combined with proportional control, so it's often called proportional plus rate control. Also, it's sometimes called proportional plus derivative, or PD control. In any case, when a process disturbance causes the input signal to a rate controller to change, the controller measures the speed or rate at which the input is changing and produces an instant boost to the proportional output signal. In effect, this action tries to stop changes in the input as soon as they're detected. To get a better understanding of rate control, we'll use this automatic level control system in which rate control has been added to a proportional controller. We'll say that a continual disturbance causes a decrease in the flow of water from the tank, which in turn causes the level in the tank to rise. If we look at a graph of the control signals from the process, we see that the rate controller responds to the disturbance by producing an immediate boost in output. This boost minimizes the water level's deviation from set point. Then, a combination of rate control and proportional control stops the water level from changing and brings it down almost to set point. However, because rate control responds only during changes in the input, and because proportional control only provides a proportional output, there may be some offset in the process variable. In other words, as long as the level is at steady state, even with offset, the rate controller will not provide a correcting output. When a process requires a rapid control action that eliminates offset, a control mode known as proportional plus reset plus rate control may be used. It combines the precise response action of reset control with the fast response action of rate control. Proportional plus reset plus rate control is sometimes called PID control. P for proportional, I for integral, which is the same as reset, and D for derivative, which is the same as rate. One example of a process that requires PID control is the gas-fired oil heating furnace represented here. During operation, oil flows through a pipe in the furnace combustion chamber. Gas flows through a valve in another pipe to a burner. As the gas burns, part of the heat that's produced is transferred through the pipe to the oil. The controlled variable is the temperature of the oil leaving the furnace. A sensing device in the oil pipe provides oil temperature readings to a temperature transmitter. The transmitter measures the temperature and provides a corresponding pneumatic signal to a controller. The controller uses that information to produce an output signal, which adjusts the control valve to regulate the furnace flame. Since the flow of oil through the pipe is reduced, there's more time for the oil to absorb heat, and its temperature increases. The control system responds by sending a larger signal to close down the control valve. This reduces the gas flow to the burner and decreases the amount of flame. As a result, less heat is transferred to the oil, and the oil temperature returns to set point. We can get a better idea of how the control system responded to the change in oil temperature by looking at the controller's input and output signals on this graph. The input signal to the controller represents the oil temperature. As the graph shows, when the temperature of the oil first began to increase, the controller immediately produced a corrective output signal that reflected the rate of change. This boost of control action stopped the temperature from changing as rapidly as it would have without rate action. As the rate portion of the controller output worked to stabilize the oil temperature, the reset portion of the output worked to return the oil temperature to set point. Soon, the combination of reset and rate control returned the oil temperature to steady state at its original set point. The final output signal also returned to steady state, but at a higher value. The higher output closed the control valve to a new setting to maintain the oil temperature at set point. In this topic, we described how reset control, rate control, and a combination of the two work in an automatic control system. Now let's try some practice questions. Not all control modes can return a controlled variable to set point after a process disturbance. However, reset control is designed to adjust the output of a proportional controller to help eliminate offset and restore original process conditions. Rate control is a control feature that responds to the speed at which a variable deviates from set point. The faster the variable changes, the greater the amount of rate control action. This graph shows the input and output signals for a control system that uses proportional plus reset plus rate, or PID control.